Hello, everyone. Welcome to our lecture, Technical Database Modeling, from the European Control Conference. And let's talk about this today. We consider these squares problems, and in particular, we're interested today in these squares problems for dynamic systems, because that is something you treated quite often, perhaps already at school, to not like exactly that, so in this matrix formulation, but the easiest version of it that you can calculate some sort of mean. And here we have the most general form in the calculation of a weighted least squares problem. And again, the setting is always the same. We start with measurements, y. We have something which is to refer to the linear static system description. So up to now, it's still static. We predict with our models n, which is in our case linear, and using some set of parameters. And in contrast to what we've seen before, now we weight each part gets weight WII, such we can consider measurement forms differently. Well, this is done using this is a situation which appears in measurements where you have outliers, in measurements which are clearly not correct. If you can sort out by means of that, so it's just a mathematical trick. The other situation appears in situations where you have some measurements, past measurements, which do not count so much, in contrast to the new ones, or you will over-amplify some sort of measurements, which is also possible with that. At the very end, you end up with a very famous least squares solution. So linear least squares solution, where you have stored in the matrix U everything you have as input, so all exciting, all the variables, all measurements of the input are stored there, step by step. So if you have n measurements, you have n rows, capital N, and then the weighting matrix W multiplied with Y, which is the measured output. So what the system gives you, and then you get the optimal value of that. That was our discussion last time. So as a special case, you find W being this identity matrix, you end up with the result, right? So quite clear that we have U transpose U with the power of -1 times U transpose Y, you get the very well-known result. It's important, by the way, to train that a little bit. So the problem is not the consideration of the proofs and that, etc. So for you, if you want to program such things, it's necessary to know what to store in which matrix, in which entry, and etc. So this is something you should train a little bit. This is a situation which appears quite often. You have a set of measurements, you're sitting in the lab, you have all these measurements, and you want to calculate some sort of linear regression line for this. It's a surface, a linear surface, which somehow represents your data, and you want to know these parameters. That's the setting. Measurements are present, inputs are present, and you can do the calculations right away. It's just matrix calculations, and of course, any computer tool can help you, in particular, in converting the various variables. By the way, as mentioned, you have here the Moore-Penrose Pseudo inverse, which already is implemented, for example, in MATLAB, which is inverse. It's the inverse of the matrix. It's in and P. The Pseudo inverse is P. Quite clear to use this, and with that you have this. situation. So data is present, and you can do the calculations for the parameters. The interesting fact is what happens if you make measurements over the entire day and you need already the results with the intermediate parts of the measurements. You don't want to wait until all measurements are available. You will want to get a first rough estimate from the very first measurements, for example. This appears very often if you want to do estimations of these parameters, for example, online. For example, you're flying, you want to estimate some parameters of an airplane or whatever you like, and you want to adapt your control strategy, for example, then it's necessary to do the estimation. And you can say, well, I need to fly a while, and then I have the measurements, and then I can calculate the control. Until then, the pilot is up to himself. So sorry, guys, only between Paris and Frankfurt, somewhere there, we can adjust our control strategy. This will not work. So the idea is it possible to make the estimation online during data comes in and data is represented? Can we have rough estimates before? And the answer is yes, it's possible, and the result is given on the next slide, which is given here. Perhaps it's important first to look at the very last line, which is given here, the bottom line, where you see the estimates. First, to explain a little bit the notation that you understand what's happening. So first of all, sorry for the numerous indices, but this is necessary. So you need indices for the measurement number. You need indices for the entry of the different matrices. You need indices for that's it, I think. It's not so much. Okay. So basically, the difference to what we had before is you have to say, okay, I have measurement 1, 2, 3, 4, 5, and I have to say, okay, that now it's measurement 6, it's measurement 7, it's measurement 8. I have to say in this position, and this is indexed over K. And of course, if I do an estimate for every time I get a measurement, I get a couple of estimates of the optimum parameter setting. So along our calculations, I get a couple of estimates. I have to identify these estimates. The first, the setting of data is present, I make an estimate. Then I get a new measurement. I can calculate a new estimate because I have new information, and so on, and so on, and so on. So I do a couple of estimates, and therefore the parameter theta is now also indexed over K, because every time we get a new estimate, we can do new measurements. We can do another estimate. We can calculate a new parameter theta, and therefore we have a K here. And the interesting fact, and that's perhaps the message I want you to take away. We can calculate the new estimate K based on the old estimate K minus 1 plus something. And my first question for a warm-up is to interpret this equation there. First, you can say to me what we have here, just in the brackets. What is it? Yes.
The error.
The error, exactly. So the new estimate is calculated based on the old estimate plus something where I somehow include the error, so the prediction error of my old model compared with the new measurement. And this makes sense, isn't it? So, so I compare what I have as new information, And then I have to to decide whether it should influence my new parameter setting, yes or no. But it's not a yes or no decision. And now the question is for you, how would you do that? If you were asked to decide whether I should include information about a deviation between my measurement, my new measurement, my new information, and my prediction of my model, when would you like to include this information very much? Under which conditions would you say, no, it's not a good idea to include it?
It depends on the part of customer measurement.
Exactly.
My model.
Exactly. So if I'm sure that this measurement is really important, if I'm sure, if I can trust the measurement, if I can trust my model, then I should include it. So there are two perspectives. If I can trust my model very much, then I should trust my model and should not include the new measurement. If I cannot trust my model, the new measurements should be included more. So there is a need of how can I trust my model, right? So we need some sort of calculation on that. Do you know some quantity which defines some sort of trust in stochastic sense? Yes.
The variance.
Exactly, the variance. So if I have something like the variance in my hand, well, I can say, yes, if the variance is large, I shouldn't trust the information of my model. If the variance of my model is small, I should trust it and include it different. So, and this is what happens exactly here. So what you have in your mind, we do it here. We try to calculate our trust and by means of the variance. And of course, it's a little bit more complicated because we do not have this one variance. We have a couple of variances because we have a couple of outputs. So it's a covariance matrix, and we have to include this. And therefore, it's mathematically a little bit more complicated, but the basic idea is exactly what we said. And then, depending on that, on my trust, I include it. So let's have a look at this KK. KK is just a matrix which, well, amplifies or does not amplify this deviation, what you mentioned exactly. And therefore, this matrix KK should, as you said, depend on the trust. It's exactly what is calculated here. KK depends on PK, and PK is the covariance matrix of our estimation. That's something we calculated already on the last slide for this. If we have all data, how large is the variance? If you remember that. We can not just estimate our optimal parameter setting, but also estimate how large the variance is, right? In a multi-variable setting, okay, we have a covariance matrix. That's only the multivariable generalization. That's all. But the basic idea is it's like that. So okay, if the covariance matrix is huge, so take it as a parameter just, and obviously KK is huge, and then obviously this parameter setting we should include the error even more. That makes sense. Of course, it depends on how much I influence my system. That's something we should bear in our mind. Why? Because if I have huge values, for example, I have a mechanical system and I really, I push pretty much against it to get information out of it, so I'm shading very much. I should take into account how much I amplify my system. So obviously it makes sense that the inputs also influence this KK value as indicated here. the more I amplify or the more I act on my system, the more I should include it. Okay, so what you see here, this KK depends obviously also on the old estimation of the covariance matrix, which then is a little bit more tricky, of course. But the basic idea is exactly like that. So it depends on how much I trust the situation, then I use, I trust my model, to be precise. The more I trust my model, I shouldn't really, I should trust my model, not the error. If I do not trust my model, I should use the measurements. Do you know something, a method, or where you have a similar situation? Have you ever heard? Might be the case for somebody who has heard different lectures already. Yes, Kalman filter. Exactly. It's the same principle like the Kalman filter. So for everybody who have not heard something about that, Kalman filter is a different strategy to estimate state variables first, not to estimate the parameters, but estimate the state of the system. It's like an observer, so the multivariable control setting. And it uses the same principle. It uses the same principle. The Kalman filter takes into account the measurements even more. The more it trusts the measurements, or vice versa, the more it has to trust the model, it does not take into account the measurements, or it shouldn't. And it's the same principle. For parameters estimation, you have the very same. So, same principle. Just as an additional remark, do you remember how the Kalman filter was deduced? Usually a very tricky calculation. Anybody? Well, it's not necessary knowledge at that point, but the basic idea is also there are two perspectives usually to calculate the Kalman filter, just as a hint for later consideration for you. One is something like similar to what we did, and one is this geometrical perspective I mentioned last lecture. With a more complicated in a product, more complicated situation because we have to deduce an overfunction, etc. It's not a topic of us. But for you, perhaps to take a note, if you hear something about the Kalman filter, please remember that because it's similar to that. Okay. Now, that part of the story, the calculation of the covariance matrix, becomes a little bit tricky, as indicated here. Well, but at the very end, what you see here, it's a combination of I try to predict first the covariance matrix by means of the old covariance matrix and new measurements. With that estimation of the covariance matrix, I can decide whether I should include the new measurements more or less in my new estimation. This is done in step 2, and in step 3, I calculate the new measurements, the new parameter estimation. So it's exactly what you said, how you would do it by intuition. Well, your intuition in mathematics is outlined here in the proof. Sorry for that, but it's just a lot of just matrix manipulation. It's not very difficult. So if you just go back, if you go through all these equations, you will find out, yes, it's not that complicated. But who the hell, who did it? How did he get this idea to do these matrix manipulations? Because you multiply from the left, from the right in a very tricky form, and at the very end, you arrive exactly at this equation setting. It's sometimes a little bit mysterious how to get the idea to do exactly this manipulation. And my answer to that is playing with matrix which is exactly that. So if you're playing, you do the calculation, wrong track, no, again, and so forth. That was the idea to get to this equation. It's but if you have the idea on the table, it's nothing mathematically difficult at that point. So if you have and it's nothing you have to learn at that point. Therefore, supplementary material. You can check whether we did the calculation correctly. That's all, and you can see, okay, it's interesting to see all the matrix manipulation that works, and hopefully we have no mistakes here in the slides. But that's the idea. Okay. So at the very end, more important for me is the basic principle at that point. So if we talk today about ChatGPT and all what these programs can do, well, the matrix manipulations, any computer tool Iceberg can do for you, and but understanding what's behind and using this principle in other circumstances is more important to you to get new ideas, and therefore for me it's more important that you understand what was written in these lines, not the specific formula. It's not so important, but it's more important to understand the principle at that point, because you can reuse it somewhere else if you have a more tricky situation. So back to that. Even more supplementary materials. What I wanted to say, where do I use this? As mentioned, it's always useful if you have, I go back to the slide where we have the formula here. It's useful also from a computational point of view. Why? Because if you look at the different calculations, you see there are matrix multiplications with vectors and matrices, obviously, here. And also you find vector matrix multiplications here. So that's something which is not so difficult for a microcontroller. And if you remember the Moore-Penrose pseudo inverse, you have to calculate really one inverse, which is of dimension pp. So if you have 50 parameters, you have to invert a 50-50 matrix, which is not so funny, and therefore just as a practical bit for the overall elimination, it's clear that we won't have to discuss something about 50-50 inverse matrix. It's more on how it works, right? But if you look carefully on this equation, you will see, yes, but here is also one inverse. You have to invert this equation. But if you look carefully at this bracket, you will see you have UK transpose, which is a row vector, a matrix, and a column vector, which gives just a real value, a single value. And sigma squared is the variance of the noise. So it's just the inverse of the real value, which is really not difficult to calculate. So from a computational point of view, you get rid of the matrix calculation, matrix inverse calculation with this procedure. This is also interesting because there is no matrix which has to be inverted, neither here nor there. The only thing which remains are matrix multiplications and matrix vector multiplications. This is from a computational point of view. If you have new systems, sometimes beneficial. Not always, depends a little bit on the practical situation. Therefore, sometimes if I have to implement that as Python code for an adaptive strategy, then it would be not just to use something like the least squares estimates we mentioned before in the slides, so it would be like a least squares thing, but using that because it's computation more efficient. Bear that in mind. That's the second reason why using that. The question which might be interesting also is, do we get, is there a guarantee that P star K is equal to the right P star, so the right variance estimation? And do the parameters theta K coincident with the right parameters? And the answer is yes for large N. They do converge. That's a proof which you find in books, but I think you believe me, the higher the number of measurements are, more it reaches the true values, and the more the estimation of the with the least squares in the least square sense with the Brochenus Floyd inverse compared to that are equal. So that's the result. Well, where we will use it, usually in adaptive control. So if you have a system and you have to identify what you have here, and you have to identify that it's online all over the time during operation, because you have a system which has where, which ages, batteries, for example, and you do exactly that. So then you apply your control strategies based on these newly estimated parameters. And this is quite typical in applications, so it's part of the control strategy. It's something we already talked about in the system dynamics and control lecture. Here is the solution. There I only said, yeah, there are some possibilities to estimate something like the parameters of a system. Here's the story. Here's the answer of the story. There I only said, believe me, it's possible. And then you adjust your parameters of the control and use it. Very typical examples are flight control systems. It's used there, but also in automatic control you find it because you have mechanical wear of materials due to friction also. Very often you have adjustments due to temperature situations. For example, if you do brake control, you have something which is included there. ABS, everybody knows it, or ESP. Well, there is a problem because usually you do not know the friction coefficient between the brake disc and due to temperature situation, and you do not know the temperature in the oil of the hydraulic pressure line, and therefore there are estimations made based on such a strategy. So simply is there's estimation. Yes.
Quick question: are they my initial interest?
Perfect. Super question. Yeah. Well, I don't get it. It's like always. It's just a rough estimate of you. So if I don't know anything, start with almost zero for the parameters. Okay, and it works. Of course, you should not use something P0 as being not a covariance matrix. So a very typical choice are just the unity matrix multiplied with some value, and then you can try your best to get a good fitting. But the initial values are unknown, of course. But a very important question, and there is a problem with these equations, which should say there's a given P0, okay, and there's a given theta M0. We should add this. by the way, it's not that, it's not a rare instance that you don't know nothing about the system. So some set of the parameters you know usually. But of course, if you're philosophically saying you have just black box, then we don't know it by definition. So we can't say anything about the parameters. That's the setting for us, which is given here. Okay, so but this is nice, but also not so nice because you might say, yes, but we should talk about dynamical systems because we are control engineering guys and girls, not static systems. It's interesting, yes, but we are interested in dynamic systems, how they evolve over time. And is it also possible to identify dynamic systems? And what we want to do right now is to transfer this knowledge into the dynamic system situation, which is even more important for our practical use later. So the question at hand is it possible to use data to identify the transfer function of a dynamical system? That's it. Because the transfer function is the setting we are interested in, which describes the system. Where there are two assumptions. First of all, the transfer function describes a linear system. So obviously, we have the linearity assumption at first. So we do not know whether the system is linear, yes or no. It's just an assumption. We can try it and see whether it fits or not. So the starting point is the linearity assumption. Second, our setting is still a discrete time version. So we are interested in the discrete time transfer function. So the Z transform version of our system. So basically, we start with the autoregressive moving average system, which usually can be described by means of YZ, so in frequency domain, if you like. Here we have the transfer function, which is given as a polynomial in the numerator and denominator. And very often the verbs, you find them abbreviated by means of VZ to the power of -1, which is just a polynomial, encapsulates the polynomial. It's a little strange because we are not used to this notation, but what is meant with is V1 Z to the power of -1 plus etc. until the end times Z to the power of -1 minus n. So that's the typical setting. What you know as the upper part being the where we multiply the upper part with UZ, that we have in time domain the right-hand side here. Right? That's just a back transform of the Z transform situation. Remember, Z to the power of -1, 2, and 3 just means time shift. Okay, so that's the only thing you have to know here. There is no mysterious things about. Okay, it's data, but it's shifted one time backwards. I don't know, here's backwards. Okay, one backwards. That's all. What do I do with one time shift backwards plus one time shift backwards times V1, V2, V2, V3, Vn, etc. So if I take Vi as the number of backward shifts over n, then it's similar to an average, right? So I add everything and multiply everything with the number of backward shifts. It's an average, therefore moving average. It's moving because if I have a new measurement, of course, I get new data, I shift it one forward and do again an average. I get the new data. So it's like always looking n steps in the past and do an average of it. Of course, I can account for like the weighted case before. I can say no, there's some outlier. It's not that important. So that's the setting. Just to explain the name. A little bit more complicated is this one, because here I get the output, which is also shifted, and this is the autoregressive part, which you'll probably know from your lectures in system, how it's called, sequencing systems. So that's what we have. We can also say, suppose, because now what's the setting? We are interested in the parameters A and B. We have data, it's given, the set of measurements of Y and U, and we want to identify, estimate, train, so always the same words, the parameters A, B, A1, A2, A3, etc., B1, B2, etc. That's the setting. It's a little bit different to what we have done in the control engineering part, because there we always say, okay, we know A and B, let's talk about what should we do with U such that Y does something. Now the setting is as follows. We want to identify the system at hand. So the car, airplane, whatever, the robot, whatever you want. Out of data. That's the typical database setting for the dynamical system. So A and B are we are seeking for, and the only thing we have is data, measurement data, Y and U. Well, let's make it very simple, because if we know the past, and first of all, if we know the first step, suppose you know of B1, B2, B3, etc., and A1, A2, etc., then you can, with this knowledge, predict the actual YK with your model, right? So you know the past values of Y, you know the past values of U, you can predict exactly the actual step. YK is always indicating the time, if you like. But if you have a sample, so it's this defined setting that if you usually have a best sample data system, the sample data system means you have sampling instances, and in the case it's not. Okay, so there's a prediction possible. Well, it seems reasonable, isn't it? It seems reasonable to compare your predicted output with your measured output, the actual measured output. Then it reads like this. You take this as a model. The idea is to compare the predicted output, which is given here, taking this as a model, compare it with the measured output, and use this as indication whether we have a good prediction via the values B1, B2, A1, A2, etc. That's the basic idea. Now we use a little bit math to collect all the things and rewrite it, and then you will have hopefully a good surprise. First of all, I use the same structure as a model. This is our prediction model. Suppose we know the parameters B, model parameters, and A, then we can encapsulate everything which we know from the past measurements, in such a matrix such a vector n transpose. So we have YK minus 1, YK minus 2, YK minus n, etc. And UK minus 1, UK minus 2, etc. And I collect all the parameters I do not know in such a parameter theta n. It's again nothing mysterious, but just the rewritten form of what we had before. So we have A1, A2 here as a parameter, so it's something like that. And now I do exactly what I said. Let's compare YM with the correct with the measured Y. Okay, so it's exactly like that. I do a comparison. I come to this picture later. I do a comparison between the actual output, the measured output, and my predicted output via this kind of model. That's it. Same trick we use for static systems, right? It's nothing new. Now, if you look carefully at this equation, you would say, hey, it's exactly the same. It's not similar, it's exactly the same. Why not using the least squares algorithm we already calculated? And the answer, yes, we can do that. And I did it. So I do exactly this measurement, y prime minus n transpose theta, and now I staple on in this matrix, in this super matrix n, all these vectors for a couple of measurements. And now it becomes a little bit weird in your head because you have now these measurements over time. And then you shift a little bit forward, and in this matrix, it shifts everything a little bit like this. It's like an old writing machine. So that's how it looks. But at the very end, if you look at it mathematically, it's just taking these vectors, put it in a super matrix, and then you have the setting, you have an output vector, you have all these values we measured in the M matrix, and well, why not calculating the least square sense optimal estimates? Then we are happy, we have the values. Crazy, isn't it? It's for a dynamic system, we get the dynamic system out of data based on that. By the way, you can also do the weighted least squares. You can also do the recursive least squares we used beforehand. Also possible, same story. So nothing special about it. Now here comes the problem. First of all, there are some problems, but we get rid of this. So perhaps no cliffhanging situation today. Let's talk about what we did here. We compare, what we did here. Perhaps this too fast here. We compare the actual output of the real system with the model predicted output, right? And the question is, what we did is we compare something of the shifted outputs via the matrix A, via this polynomial A. It just says you take as inputs the shifted outputs and also the shifted inputs which are given to the real system, and then we build this kind of error E. And this is somehow different to the picture we draw before in the static case. I go back to that just to inform you. It's somehow different, and then you tell me where it's different. That's the picture we did in the static case. What is different? Yes, please.
Much of the output.
Exactly. So we have here something where the output is shifted. Here we compare the output error, and there I compare something mysterious, which I do not know. So going back to our slide. And we have to talk about, well, does it change the story a little bit? And unfortunately, the answer is yes. So we do not compare the outputs directly, but something else. And is this perhaps a problem? That's the question. Let's first have a look at the problem itself. Just to make it explicit, what I do here, and then we come back to this question. Okay. What we do here, M is given, and somebody draws this matrix in a full form, and it looks like this. The interesting fact is, it's interesting. There's a story behind that. this matrix has been presented in books over decades. And during my PhD phase, I was responsible for such a lecture of my predecessor. And there was one student who did all the calculations by himself. So I was persuaded by I never did too much work. And he said there's a mistake. And really, there was a mistake. The matrix was wrong over years and books. Nobody realized it. This is something you realize only if you implement the situation. There were a couple of mistakes, by the way. Well, the question why it's interesting, because I want to show you what is M. I want to show you what we have in our hands to give you a little bit more insight into the problem. Let's have a look perhaps at this particular part here, this one, on this slide here. I highlighted it a little bit to that you can see it. So if you look at this matrix, this sum, do you see something which you have already seen before? If you look at this sum, you have discrete time values of u, which are somehow multiplied with discrete time values of y. No? It's convolution, exactly. Is it exactly the convolution you learned? Signals and systems? If Michael enters the room, he would say, hey, you're crazy. There's something wrong with it. There's something missing. If you remember convolution, so even in the continuous time, convolution or integral, which are what is the integral?
The complex number.
Yeah, might be complex. Yeah, this is one. Something else. If the convolution integral, I have never the sums in my mind, but what is the interval, the convolution of integral works in plus infinity, and the discrete time case it's the same. Do we have this here? No. This is different. But more or less, it's close to the convolution integral. What is also close to the convolution integral? And not the convolution integral, but also the time domain. But you see also more in the stochastic version of it. Correlation. Exactly. It's correlation, it's cross correlation of these here. So the question, what is calculated here is the cross correlation between u and y. And but not between u and y, but between u and y shifted by n-2. So that's what we see here. So the matrix M represents cross correlation coefficients, which you find over here and here, and autocorrelation coefficients of u over here and there. So we can. And the interesting fact is, the same is true for y, the same is true for m transpose times y. The interesting fact is that if you look at this, you get an approximation of the autocorrelation and cross-correlation coefficients, and these matrices read as follows. They are just a matrix of cross-correlation or correlation coefficients of the various signals at different shifting distances. So if you compare whether this signal is similar to that signal, shifted 1 step, 2 steps, 3 steps, etc. This also makes sense in terms of what we are doing here. Of course, it if signals are more correlated, it must have impact on the parameters, right? So it makes sense from an intuitional point of view. And that's why it is in here. So please never learn this by heart. It's not so important. So just big attention sign. But the basic idea behind that, the correlation plays an important role in defining or determining the optimal parameters is important. And it's a second important thing. Why it's interesting to have these correlation calculation, more from a computation point of view. Now, I'll link to it. Do you know which kind of computer is capable to calculate correlation easily? No. Is it? Do you know? I do. I started differently. I started with the question of, leave it as it is. A DSP. So digital signal processor is capable to calculate what easily Fourier transforms, fast Fourier transforms, and these values can easily be calculated with fast Fourier transforms. Why it's important? Because if you do such kind of estimates, you need a machine which is capable to do calculations of cross correlation, autocorrelation coefficients. And if you don't want to do this online, then DSPs are very helpful. Therefore, the second is also interesting. Okay, so this is perhaps the first part of the story. So understanding the situation is okay. The parameters are calculated that way, but you already said, okay, there is a problem perhaps because we have a dependence on past values. Back to my question, do we have a problem? We have this mysterious E, and in which go back to this slide here. We do not calculate the output error. We do calculate something different. And this, in which way it's different? Well, we also use past values of Y, which is somehow symbolized by A to of Z to the power of minus 1. And I want to show what happens. Well, we did the calculation of theta m. So what question has to be asked whether we should be happy with this calculation, yes or no? When do we define an estimation to be good? In that sense. So the error between the true parameters and the estimated parameters is almost zero. This is one part, and the second. What's about the trust? We should also trust the parameters we estimated. So if we can trust that if the variance is quite high, we can trust our estimation, then it's also problematic. So there are also these two parts we check. How do we get the right parameters? This is bias free in that sense. And so right means our parameters exactly the true parameters of the true system. First answer, and then we trust them. The second, and this is encapsulated in word. This is something you should put in your head. Like this is the word consistency. So if it's consistent, then it's good. And consistency is guaranteed if it's bias free and the variance is limited. So it's good things. If it's infinite, if we can't trust the parameters, of course it's not a good estimate. Okay, this makes sense. So the question is, yes, we get this. The answer squirrels around the question whether the estimation is consistent, yes or no. And unfortunately, I have to say it's not consistent. Here's the answer. So first of all, we looked at this real system, which is given here. And now we want to describe what we are doing. We want to rewrite E, our mysterious error, which we use for calculation of the parameters. And we want to describe this parameter E, this error E. And for example, we can say, okay, our true system is given by means of you entering the system, which gives X, plus some disturbance. In our case, we make it as in the regression part, we say, okay, this is white noise, for example. Because we know if for the static system, we already realized that if it's white noise, then we get a consistent estimation. So the question is this the same here? And let's have a look. Here you find the equation which just calculates this thing here on the right hand side depicted. So first of all, we get y as the summation of the system output plus the white noise. And the error itself is calculated as the one-step prediction of our model, subtracted from our measurement output. That's it. So now I enter everything. Here we have xk plus epsilon k plus a1 xk minus 1. This must be a, there's a typo. Copy paste. Here. Should be really a typo. No, it's okay. It's okay. Sorry. I was mistaken because we have to write down y and not just the xk values. That's true. So we get a summation of the predicted output, which is given here, and if we use our calculation from before, we get exactly that for each type. So we can write it down that xk is equal to that. This is just the system equation. And we find out that ek is exactly that. So the question is, what kind of ek do we have here? Now assume epsilon k is white noise. Is ek then white noise? So epsilon k is white noise, so nothing is correlated. And now I put everything in such a formula to calculate ek, and the question is still white noise? Just a simple argument.
Ek dependent on epsilon k, which is the other error that is white noise.
So it can't be white noise. Exactly, because obviously epsilon k enters here, and there I shifted a little bit. So in probability, I have a dependence between epsilon k minus 1 and epsilon k. So ek can't be white noise. Consequently, we can say there is a high probability, to be precise, as usually it's a high probability that the estimation is not biased, because if you remember, in the steady case, we ended up with the result if epsilon is white noise, then we get a bias-free estimate. Unfortunately, E, which is the counterpart for epsilon in the static case, is not white noise. That's the problem. We can also, putting it in this form, this is a positive formulation, by the way. here you have some sort of proposition which says under which condition it is under which condition the estimation is by 3, and the answer is under the specific condition of the disturbance. So what I wanted to say is there are only rare instances where we have a bias free estimate if the output is disturbed by means of any of a white noise simulation, because we do not have white noise as the output. We can put it differently. You can say only if the true output is affected by means of a disturbance which looks at like this, where the disturbance has a specific form of noise, where eta is white noise. It is a filtered white noise, which is colored noise, what you know, right? Filtered white noise is called colored noise. Then we have a bias free estimate. So now let's put a little practical point of view on this problem. And the question is, does this exist? And the answer is no, usually not. There are some cases where it exists, but in most cases it does not exist. So, and this can be made clear in this picture. The question is, so what the proposition says is, I put it somewhere here. The proposition says, I have the input, U. I have here my true system. I have my intermediate variable, UK, XK. I add something, epsilon, okay. I get the output, YK. And only in the case where this is affected by a filter, which is given here and there, we have white noise. Then we get a bias-free estimate. Well, now the question is, 1 over a z to the power of -1 is the filter. We do know the filter, how it should look like. But the question is it possible to affect the disturbance of the true system? By the way, the true system looks like this, the entire. So this is perhaps the, let's see. This is the true system. So the question is it possible to enter a filter in the disturbances, epsilon, which looks like 1 over a? Question for you. What do you think? Who thinks it's yes? Again. 1. Who thinks no? Majority. Who has no answer at all? Of the majority. Well, it's always important not just the answer is no. And I will explain why. It's always good to understand what you have in your hands. What is responsible for having disturbances at the output practically? What affects the output disturbances? It's responsible for that, that we have white noise at the output, that we have not perfect measurements. The measurement system itself. So, what is responsible for having white noise and for example, for a voltage meter or some temperature. So, what exactly? Even deeper. You're right. Everything is a phase. So temperature affects exactly that. So what is who is responsible for noise at the measurement device? Practically. Sorry. Exactly. What describes the movement of the electrons? Do you know that? In terms of temperature, some sort of Brownian motion. So, it's not important for our lecture, just to what is meant with, if you want to include a filter here, just to make it explicit, is saying, hey, electron, move differently. That's exactly what is meant with the filter. So you have to enter into the noise process and say, well, behave differently in the physical object. And the physical object is the voltage meter or ampermeter or whatever it is. Yeah? And usually you cannot enter in the electron's head and say, no, I want to bias free estimate, please use differently. That's not possible. So please be clear, this is inside of your system, in your measurement device, so consequently you can't enter some filters in it. Therefore, it's like it is. And in particular, when you need a specific filter, basically a filter which depends on the system. So sometimes you would say, yes, of course, it's the color noise due to temperature, high temperature, less important, lower temperature, more important, etc. So it's usually it's not a white noise process, but the color noise by itself. But is it exactly that color noise we want to have? No, because you use the same ampermeter. I have to start differently. A is something which depends on the system itself. So whether A describes whether it's a car, robot, process machine, whatever, but you always use the same ampermeter or the same voltage meter or the same velocity meter, whatever. So consequently, it can't be the case that the noise of the ampermeter depends on A. It depends on the system drivers. This is also not the case. As an answer, so usually we don't have the situation that we get a bias-free estimate. Now here comes the engineering trick. Under which condition do we get the bias-free estimate? Under which specific examples you wouldn't get a bias-free estimate if you look at the situation. Here's the trivial, perhaps. Yeah. Exactly. So if the noise is small, say like this. So engineering, this is practical engineering, saying, so if your situation is as that the noise values of the power values are small, you can be happy, you can use this, because then it will not affect your solution. We will calculate how large the error is, etc. in a second, and then you will see, okay, it's small in that case. This is the first one. So if you have not so much noise, then please use that. It's easy. But there is a second case. If it's, yeah, sometimes it may fit to what you need. Second, so check this, and then I will say it's the third one I had in mind. Suppose eta is white noise, and under which condition epsilon is also white noise, because then we are happy. Exactly, if A is 1, white noise goes to white noise. Now let's have a look what it means A is equal to 1. Well, here is A. If all these coefficients vanish, right? Second, what remains? Just B. What is it? It's kind of description of the system. The question is very tricky. Which part of the Armor system remains? R or Ma? Yes. It's just a moving average. So if you have just a moving average system, you're happy. So this works for moving average systems perfectly for small amplified noises and perfect fitting noises. Okay, 3 cases. The latter case is rare. The others might appear in engineering. So if you have a moving average situation, everything is happy, then you can be happy. If you have a small noise values, also okay. And the case where A is really filtered that way, or the noise is filtered that way, it's not so often, and in that case we need something else. So that's important. Just to conclude my my consideration, I want to say how large the error is, and this can be calculated even here. If you calculate the estimation error, which I did here on the slides, this is not very complicated. We end up with this here. This is something we did already, and the estimation error and the variance of the estimation as well, also not complicated calculations, just to show. And here is the important theory. If this proposition 5.3 is fulfilled, the linear least square for dynamic system is consistent, but this is not always the case as given. So we can say, okay, it's possible. It's a positive result, but it's not very helpful. This, by the way, because we are in a master class, by the way, is the typical way researchers present their research results. Always positive. If during your master thesis you will read research papers and you will think, hey, it's already done, it's perfect, it's super, it's excellent, because they present it that way. They say, so if this is given, then you get a good result. But if you think of the assumptions and stress them a little bit, you realize, yes, but there's a problem from a practical point of view. So always be careful or read the assumptions about that. It's a typical way how research is presented, because we have a positive way of how research enters a community. And sometimes it's a little bit frustration when you start your career, and this starts in the bachelor and the master, and you read the papers and you see, ooh, it's so positive, it's already done, and what a smart guy, he's so good. Usually there are no calculation mistakes, only in poor journals, but usually there are no calculation mistakes, but the assumptions are too strong, too difficult to fulfill. The situation, the setting is perhaps not practical. And you as engineers are capable to say, yes, I can I can judge whether this is a good situation or a bad situation. So always have to keep that in mind, perhaps for your later use. But we are left with this nice theorem. This is nice that we can end here because for practical reasons, we have the situation where we can say to the electron, please move differently. It's not possible. So the question is there a procedure which allows for a different way of calculating the estimates such that we circumvent this problem, right? And the answer is yes, there is something in that set. I want to check, yes. Before we start that, I want to stop here. First of all, there are a couple of questions about whether we can identify the parameters. It's the same thing as before. Is it possible to get the results? Remember our considerations about the Moore-Penrose pseudo-inverse. It must exist, must be invertible, etc., etc. Similar results exist also for dynamic systems. I put here, there's a, vast literature. A substantial amount of work has been done in that area about whether we can identify a system, the theoretical considerations, and define initial results and important results here. So if you're interested in this supplementary material, please feel free to read it. There's also at the very end a nice link to observability and controllability of systems and stability, which basically say if the system is observable, controllable, and stable, then we can identify the system by means of such squares. Estimation procedures, for example. That's interesting, but out of the scope of this lecture, and therefore just added as additional knowledge. Second thing I want to do, and I want to give you room and enough time, because I forgot that all the time. Usually I do it digitally, the questionnaires, you know. But due to the fact that this has not been done at the right time, I always had the digital version with me, the paper version with me, and always forgot through my course to give you the opportunity to answer. Please, in this case, it's pure analog. Fill it out. I will be very, very, very happy if you add comments at the very end. It's always helpful for us to optimize selector. Perhaps I distribute that here from the first row. Perhaps you can give it to your neighbors. Here. And then I would be happy if there is a volunteer for bringing this to the quality office. Is there somebody who likes to do that? Yes, thank you very much.